Hello everyone. So I will be presenting to you a new tool I developed called Sniffle, which is a sniffer for Bluetooth 5. So I created Sniffle because there already are quite a few sniffers for Bluetooth LE out there, but there was nothing that worked quite the way I wanted it. The existing low-cost sniffers, they, apart from certain feature limitations, they also sniff only one of the primary advertising channels at a time, and so inherently they're limited to less than 33% reliability, and beyond that they're also missing some features I wanted. So what Sniffle is it is a Bluetooth low-energy packet sniffer that includes support for all the improvements in Bluetooth 5 that runs on TI CC26x2 and CC13x2 microcontrollers. So out of the box, the firmware is set to run on these development boards here. These boards, they are about $40 US, and the firmware, it runs on this little processor here, and you could have any other device that has the same microcontroller. You could program it to run this firmware, but the easiest device you can get your hands on are one of these development boards, which are available on TI's website and various electronics resellers as well. So Sniffle supports almost all the new features in Bluetooth 5, including the new PHY modes for long range and high speed, and it also supports extensions to advertising in Bluetooth 5. Sniffle can display packets to your terminal in real time, and it can also record data to PCAP files for later analysis or viewing in Wireshark, or if you want to pass them to Crackle for decryption or anything like that. And the biggest benefit Sniffle brings over existing low-cost sniffers is its ability to capture advertisements from all three primary advertising channels using a single sniffer. And this makes it vastly more reliable than other low-cost sniffers. In a room like this, where there's a lot of Bluetooth devices out there, any sniffer's reliability would likely degrade. We'll see how it does in the demo. However, in a quieter environment, Sniffle gets over 90% reliability in my testing for connection detection. So, for those of you who don't know too much about the different kinds of Bluetooth, there are two distinct protocols that are both called Bluetooth. There's Bluetooth Classic and there's Bluetooth Low Energy. So, in the middle of the protocol stack, there is what's called a host controller interface, or HCI, and that is the interface between the Bluetooth controller chip and the main host processor. And that is common between Classic and LE. There's also L2CAP, the link layer control and adaptation protocol. This is also common between LE and Classic. However, apart from that, all the profiles at the higher levels of the stack and the physical layer below these are completely different. It's different modulation, different channel hopping schemes, different PDU types, different pairing processes. They're just essentially different protocols, both called Bluetooth. What's also in common between these is that they're both frequency hopping, and they're operating the 2.4 gigahertz band. At this point, Classic exists mainly for... It was the original Bluetooth, and it's commonly used for audio streaming devices like headphones, or also for calling in cars, as well as things like the phone book and message access profiles for automotive applications. These profiles are still used because there's a huge amount of devices that support them, and I suppose the Bluetooth SIG didn't want to reinvent the wheel with yet another incompatible standard. However, all the development effort in the past few years has been focused on the low energy side of the spec, and most IoT devices we encounter nowadays use Bluetooth LE. Both the Classic and the low energy part are both part of the Bluetooth 5 standard. However, there were no significant changes to the classic side of the spec. Bluetooth 5's enhancements focus mainly on the low energy side. And as a result, when you often hear of Bluetooth 5 devices, they omit the word low energy because what's new in Bluetooth 5 is the low energy side. So the Bluetooth low energy spec was originally introduced in 2010 as part of Bluetooth 4.0. And back then, it was intended only for low bandwidth applications that don't have a lot of data to transfer. It strictly limited the size of packets you could send, and it had a slower PHY than Classic. So Classic supports, in addition to a 1 megabit mode, it also supports 2 megabit and 3 megabit per second enhanced data rate modes, whereas historically Bluetooth LE only supported 1 megabit mode, and furthermore the bandwidth was hampered by the short packet size. Now, Bluetooth LE, both in the original 4.0 form and even in the current form, divides the 2.4 gigahertz spectrum into 40 channels, of which the logical channel numbers 0 to 36 are for data transfer, and channels 37 to 39 are for advertising so that other devices can be discovered. Now, one thing to note is that these channel numbers are not strictly sequential. Channel 37 is actually the lowest frequency. Channel 38 is in the middle, in between the data channels, and 39 is the highest. But they group them like this just so group channels are, well, similar applications are lumped together. Now, at the higher levels of the protocol stack, there is the generic attribute protocol, or GATT. And GATT, to the user, Bluetooth peripherals will have a number of what are called characteristics that a client can write to, read from, or subscribe to notifications on. In Bluetooth 4.0 and 4.1, they had a very weak pairing process that relied on symmetric cryptography, and as a result of this, there's a lot of research published on ways you could defeat the pairing process if you were able to sniff the key exchange. In Bluetooth 4.2, there was a new pairing process introduced that uses elliptic curve Diffie-Hellman key exchange. There were some issues in this too, in the spec not requiring that points in the curve are properly verified, but this has been addressed. However, the new elliptic curve pairing process is not mandatory. So there are a lot of devices that still make use of the legacy pairing process that's weak. And also many devices that do support the elliptic curve pairing allow fallback to the legacy pairing process. So this is a common issue we see. Bluetooth 4.2 also introduced an important feature called data length extension, and this greatly increased the bandwidth of the protocol just by greatly reducing the fraction of time spent in overhead. So it increased the max size of a data packet from 31 bytes up to 255 bytes, and that increased data throughput something 5 or 6-fold. Now, Bluetooth 5, which is quite new, was introduced in 2017 and further extended Bluetooth LE to have performance similar to, or sometimes better than, Bluetooth Classic. So one of the improvements is that it introduced a new PHY mode that has faster modulation, 2 megabits per second, and this allows transferring a lot more data through it. They also introduced PHY modes for long-range communication with forward error correction. So these actually use the 1 megabit per second modulation, but there is an excessive amount of data sent on them that's redundant so that you could recover the original data even if there was some corruption when the data was transmitted over a long range. Another change in Bluetooth 5 is a new channel hopping algorithm. The old channel hopping algorithm you started on one channel and there was just a number called a hop increment. So the next channel number is just the last channel number plus the hop increment modulo the number of channels. There was another scheme for when a channel was disabled from the map, but overall was fairly simple. The new hopping algorithm is based on a pseudo-random number generator. It's not meant as a security feature, but what it does intend to do is reduce the chance of repeated collisions between Bluetooth devices. A very large change in Bluetooth 5 is the extensions to advertising. So advertising is the process through which Bluetooth devices say that they are here and they can be connected to, or they have information available for you to scan. In Bluetooth 4, advertisements were limited to 37 bytes, and the advertisements had to go on the 3 primary channels. Now, the issue for that was that in very crowded environments like the room we're in right now, there was a high chance of collisions between all these different devices trying to transmit advertisements at the same time. So they tried to keep advertisements short with this length limit, but even then, collisions were an issue in crowded environments. So what they did in Bluetooth 5 is they allowed very short advertisements to be sent on the 3 primary advertising channels that point to a data channel that's channels 0 to 36, and you can transmit a much larger piece of data on one of these data channels without hogging the shared primary advertising channels. There's also a new process for establishing a connection on these data channels instead of doing it on the primary channels that tend to be very crowded. In Bluetooth 5.1, which just came out this year, there was a couple more optional features that are called angle of arrival and angle of departure. Those are used for determining the direction in which data is coming from. If you have an array of antennas receiving or an array of antennas transmitting, by looking at phase differences, you can perform some triangulation. And the other noteworthy change in Bluetooth 5.1 is that it allows randomizing the order in which you advertise on the 3 primary channels. Now, one thing to note is that all these new features in Bluetooth 5 are all optional. And as a result, there are a lot of devices you see on the market that claim to support Bluetooth 5, but they only support a small fraction of these, or sometimes none of these new features. As technically a valid Bluetooth 4 device is also a valid Bluetooth 5 device. You just have to go through the certification process again, and you can just say, oh, I don't support any of these new features. And as a result, there's a lot of phones in the market. It took me a lot of research to be able to find a phone that actually supports Bluetooth 5, as there are a lot of phones that claim they support Bluetooth 5 and they may support one or none of these features. So, with the existing sniffers, one of the biggest frustrations you have with these low-cost ones is that they only sniff one advertising channel at a time. And even in the legacy connection establishment procedure, which is still the norm for almost all Bluetooth devices you encounter currently, the connection will be established on one of the 3 channels. And if you're sniffing only one of these channels, then there's only a 33% chance you'll catch it. Add to that, there's imperfect fine-tuning on many of these sniffers, and your reliability slips well below 30%. So it can be just quite frustrating to have to try 3 or 4 times to be able to detect connection establishment. And sometimes if you wanted to capture a rare packet that's hard to reproduce, it's just a big frustration. The other issue with the existing low-cost sniffers is that there's nothing with comprehensive support for Bluetooth 5. When I started this project last year, there was nothing remotely affordable that supported Bluetooth 5. Since then, Nordic has released an update to their NRF52 sniffer firmware that supports the 2 megabit PHY mode, but nothing else in Bluetooth 5. Another issue that with many of these low-cost sniffers, not all of them, but some of them have proprietary firmware and software, and sometimes they're Windows only, sometimes they force you to use an outdated version of Wireshark, sometimes they're hard to extend or integrate with other things. And the sniffers that were better and didn't have this limitation of only sniffing one channel at a time are very expensive. They're thousands of dollars, sometimes tens of thousands of dollars. So what Sniffle does is that it uses the very flexible radio hardware in the TI CC13x2 and 26x2 microcontrollers. They're largely the same, except the 13x2 also supports sub 1 gigahertz the communication in addition to 2.4 gigahertz. It uses these radios to tune into the various Bluetooth channels, configures the modulation on them, and my firmware that runs on the microcontroller with these flexible radios controls the radios to capture all the Bluetooth traffic of interest. So they can capture advertisements in the advertising channels, or if there's extended advertising, it'll hop from the primary advertising channels to the data channels to gather those advertisements. And if you have it configured to follow connections, then when it detects connections established and it matches all the filters like a MAC filter, then it will hop along with the connection and capture all the communications between two devices. So for filtering, it can filter both by the MAC address of the target as well as the RSSI. So often, if you're in a building with a lot of people, you'll see a huge number of Bluetooth devices and a lot of noise that you're not interested in. So if you just place a sniffer near the device you're interested in, you can just set up the RSSI filter and only capture the devices that are nearby that are more interesting. The Sniffle does support updates to connection parameters during connection, things like the hop parameters, the channel map, and the PHY mode. A lot of sniffers don't support this or have incomplete implementation of this, and this greatly limits reliability and usability again. So the fact that it supports these things ensures that it will always follow your connection even when the RF environment changes and connection parameters are updated as a result. The Sniffle firmware communicates with the host over UART. On these development boards, the TI board I showed earlier, there is a debugger chip that includes a USB to UART bridge. So when you plug it into your computer, it'll be a USB port, but it's the USB UART. And then I have host-side software written in Python that will display the traffic, do some decoding of it, as well as writing it to a PCAP file. And I wrote it in a manner where if you want to extend it, it's quite easy to do. It's a fairly simple API for it. Now, the killer feature of Sniffle is its ability to hop along with advertising on 3 primary channels. So the Bluetooth 5.0 core spec in this is one bit that was never really publicized much, but the spec requires that when you advertise on the primary channels, you do it in order of 37, 38, and 39. The spec says that you must start with the lowest channel index for primary advertising and then end with the highest index. And I did some research. Well, I had a bunch of Bluetooth devices around. I was trying to see if the timing was fairly predictable. The spec does not enforce the timing between when you advertise on 37 and when you advertise on 38, but I found that different devices may put a different amount of gap between these. However, it's generally consistent for a device. Now, the exception to this is when you receive a scan request. So what a scan request and response is that if you have an advertisement with a small amount of information and a scanner is interested in that device, it can request additional information with a scan request. And when there is a scan request, the time spent on an advertising channel is extended. However, when there is no scan request, then there'll be some fixed amount of time that devices in practice will spend on each of the primary advertising channels. And when you detect the scan request, you can adjust for it by just adding some time to postponing the hop to the next channel. So this is what Sniffle does. One other thing is that in the previous diagram, what I showed was an advertising event. So for the legacy style of advertising, which is still what most devices use today, an advertising event will advertise on 37, 38, and 39, and then the device will stop advertising for some period of time, and then again in short succession advertise on 37, 38, and 39. Now, the gap between these advertising events is intentionally randomized by the spec to reduce the chance of collisions. And as a result of that, you can't predict in advance when the next advertising event is going to happen. So what Sniffle does is that it will wait in 37 once it has figured out the hopping pattern, and the moment it gets an advertisement 37, then it knows an advertising event started and then begins the hop process. So by doing this channel hopping, Sniffle can capture connection establishment with over 90% reliability, at least in a more calm RF environment. And having performed some analysis on previous hopping patterns, once Sniffle figures out the hopping pattern, then it will just lock on and do the 37, 38, 39 hop every time it gets an advertisement on 37. And when the scan request is received, then it'll just extend the time spent on a channel. So this here explains the algorithm for the hopping, though I've largely already explained it. Well, the first step before you do this, though, is figuring out how you're going to be hopping. So to do this, what Sniffle does is it waits on channel 37. When it gets an advertisement on channel 37, it immediately jumps to 39, skipping 38. This is mainly for performance reasons, as often the advertisement 38 will come very soon after 39, and there's a chance you'll miss that initial advertisement in 38. So it'll hop from 37 to 39 the moment it receives an advertisement channel 39, and waits for a second advertisement with the same MAC address you're interested in. And it'll do this repeatedly and record the timing between an advertisement on 37 and 39. And once you have a bunch of samples, some of these will be including scan requests, and others will not. So you'll see generally a bimodal distribution of timings. You'll see some timings that are short and some timings that are long. So that's why I don't just take the median of the results, but I chose to take the 25th percentile of the timings I captured, and then I divide that by 2 to get the time between two channels as I captured from 37 to 39, so 37 to 38 will be half the time. So once I have that interval, then I do the hopping process I described earlier. We're waiting 37. When you get it on 37, then do 38 and 39. This works great. However, Bluetooth 5.1, which just came out this year, made life a little more difficult as it allows randomizing this. Fortunately, in Bluetooth 5, the new extended advertising process doesn't establish connections on the primary channels. Instead, the connection is established on the secondary or auxiliary advertising channel. As a result, if you captured the short advertisement on any of the 3 primary advertising channels, you'll then hop to the secondary channel, as all 3 primary advertisements will point to the same secondary advertisement, and when you are listing on the secondary channel, you will capture connection establishment. So Bluetooth 5.1 shouldn't pose an issue just because Bluetooth 5.1 devices are likely to use the new connection establishment procedure. For the extended advertising feature, you have a short advertisement on your primary channel that just specifies a time offset, the channel that you want to do the extended advertisement on, and the PHY mode you're going to use for it. So it could be that you're using the 1 megabit per second PHY on the primary advertising channel and a 2 megabit per second PHY on the secondary channel. And so Sniffle will, when it receives a short advertisement indicating there's going to be an advertisement on the secondary advertising channel, then it will schedule a hop to that channel on the correct PHY mode when the time comes. Once it hops to there, then it will capture any advertisements there and connection establishment as needed. One big advantage of this is that now you can advertise with long amounts of data, up to 255 bytes in length, and you can actually go even longer according to the spec. You're allowed to chain multiple advertisements together if you had a really large amount of data you want to transfer. Support for this in Bluetooth stacks varies. iOS only supports, I think, 128 bytes for extended advertisements. Android's limited to 255 bytes, though in theory the spec allows chaining these. Now, there's also another feature called periodic advertising, which is for what's sometimes called connectionless data streaming, where it's multicast streaming of data to devices that don't have to establish a one-to-one connection. In this process, devices are transmitting advertisements on the primary advertising channels, continuously hopping between them, and there'll be one advertisement that provides information sync along with this hopping sequence of advertisements on these secondary channels. I have not encountered any devices that currently use this new feature, and a lot of devices, a lot of Bluetooth stacks don't even support this, but it may become popular at some point in the future. The main benefit of this new advertising is that it reduces a chance of conflicts on the primary advertising channels and allows transmitting much longer advertisements on these secondary channels. So Sniffle will schedule the channel hopping and capture advertisements on the auxiliary channels, and it'll also follow connections established on these channels. I have not implemented support for periodic advertising, partly because it's poorly specified in the specification. The specification doesn't even say how you're supposed to do the channel hopping. It leaves it up to vendors to implement, so I assume vendors will make some sort of standard of their own for this. And since hardly anything is implementing this right now, I didn't see a reason to spend too much time on it for now. So when you're dealing with a Bluetooth device, your options are either to you do HCI logging or use a sniffer. Now, when HCI logging is possible, that's usually preferred as it's the most reliable approach. As an example, if you have an Android phone that's talking to some IoT device, you can configure HCI logging on the Android phone, and that will capture all the communications between the Fluoride or Blue Droid stack on the Android phone and the Bluetooth controller that's actually interfacing with your device. Now, one limitation of HCI logging is that what's going over the HCI is not what's going over the air. The Bluetooth controller is performing a number of transformations, including encryption. You also have no visibility into the lower level link layer things. It's just a black box to the host side of things. And also, if you're trying to troubleshoot issues in a Bluetooth controller or troubleshoot a custom Bluetooth stack, or trying to find bugs in these things, it's useful to have lower level capture. The other situation where you can't do HCI logging is if you have two embedded devices where you don't have much control of either of them and they're communicating with each other over Bluetooth LE. We've encountered this a bunch of times. In these situations, your only option is to use a sniffer to see what these two devices are doing between each other. For Bluetooth Classic, sniffers are quite expensive. The only Bluetooth Classic sniffer I know of that's vaguely affordable, that's affordable is the Ubertooth. However, Ubertooth's Bluetooth Classic support is very limited, and Bluetooth Classic, part of the reason it's difficult to build classic sniffers is that they are very fast channel hopping that makes synchronization a little tricky. So you can see here in this chart why I made Sniffle. So there's a whole bunch of existing sniffers. There's the Ubertooth. There were a couple free sniffers made by TI, both their previous generation and their current one. Nordic, which is the other popular maker of Bluetooth microcontrollers, they have a sniffer firmware that runs in both their older NR51 and their newer NR52 series devices. And there is also another researcher, a friend of mine, Damien Coqui, who had made a tool called Beetlejack, which has a cool feature of connection hijacking in addition to sniffer capabilities. But the issues with these, some of them, particularly older ones, don't support data length extension. Almost none of these support the new PHY modes in Bluetooth 5. So the only one other than Sniffle that partly supports Bluetooth 5 PHY modes is the Nordic one, but it doesn't support the long-range PHY. Most of these don't support the new channel hopping. None of these support the new Bluetooth 5 advertising extensions. And most importantly, none of these will sniff all 3 advertising channels at once, unless you're running multiple sniffers, which can be a little cumbersome at times. So with these extra abilities, Sniffle becomes a lot more usable for newer applications. And with these capabilities, Sniffle becomes a viable alternative to much fancier commercial systems. So in the past, if you wanted reliable Bluetooth LE capture, you had to resort to systems that cost thousands of dollars. And if you're not working in Bluetooth all the time, if you're just an independent security researcher, you're just a small-time startup building products, you often can't afford tools like this. And these high-end sniffers are powerful and good. They're probably more compliant with the spec than my sniffer is, and some of these have nice features like the Elysis and the Teledyne Frontline Sodera wideband models. These are actually software-defined radios that can capture the entire 2.4 gigahertz spectrum, and that's very expensive in terms of the hardware and processing power, so the costs aren't fully unjustified. However, with Sniffle, just with some clever channel hopping techniques, you can get comparable reliability for a tiny fraction of the cost. So Sniffle is available on GitHub now. It's GPL v3 license. Do whatever you want with it under the license. On the README for the Git repo, I have instructions for setting it up. I also have some pre-built firmware binaries available for those who don't want to set up a tool chain. It's compiled with GCC. Also, if you're working with Bluetooth Classic ever and want to test some profiles that are built on top of Object Exchange, so OBEX is the base for a whole number of other profiles like file transfer profile, object push profile, message access profile, phone book access profile, and some others. Or if you're testing automotive head units, you can also check out my Nobex tool. So I will give you a little demo of what Sniffle can do, and hopefully it will cooperate in this crowded room. So, just as a demo, what I'll do is I'll set up one phone as a Bluetooth advertiser, and that can also be connected to, and then I will have my other phone connect to it, and we can see if Sniffle can capture them communicating with each other. So the first step is that you need to find the MAC address of your target. So let's see where I put them. I'll leave them on the ground. There. So for this, what I'll do is I'll set up an RSSI filter, and then I'll set the RSSI threshold to a fairly high, strong signal, and then I'll place my phone that's acting as a Bluetooth advertiser nearby so that you can see its advertisements. So without specifying any additional options, then it's just listening on channel 37 on the default 1 megabit per second PHY. So if I put this nearby, there we're capturing a bunch of things, and I can grab the MAC address, which is right here, and now I can configure the radio to lock onto this MAC address, and now I don't need the RSSI filter since I know the MAC. And now what the sniffer will do is that, so it's capturing these advertisements, and initially it's just figuring out the hop pattern, and once it's figured out the hop pattern, it'll start hopping along with the advertiser. And now, I have my other device here. I will scan for this and try connecting to it. Okay. There, it connected, and it's capturing all the communications here. I forgot to turn on PCAP writing, but I recorded another PCAP file earlier. And to demonstrate the reliability of this, I could try disconnecting. Connection ended, And if I try connecting again, hopefully it'll capture it. There, captured a second connection establishment. Well, let's see if I can get 3 out of 3. 3 out of 3. That's a lot more reliable than most of the other sniffers out there, even in a crowded room like this. So, I can also give you one other little demo, which is capturing extended advertising. Then I'll stop this guy advertising. So, didn't mean to put it to sleep. So here the -L option means to use the long-range PHY, and -E means enable extended advertising. So if I do this here, and then I start my advertiser, you can see it's capturing these advertisements, and you can see that, so this here, on channel 37, is an extended advertisement that's pointing to channel 34, the 2 megabit PHY, and the advertisement will come at an offset of 107,000 microseconds. And so it tunes to this other channel and captures the advertisements there. And if some other device was trying to connect to this, then it'll capture the connection establishment and hop along with it. And there is no other sniffer that's not thousands of dollars that can do this right now. So that's it. Do you have any questions?
What type of demo board you will recommend from TI, based on 13 or on 26? Which is better?
13 is better, is it has all the capabilities of the 26 series, but it also adds support for sub 1 meg PHYs. So for Sniffle, it makes no difference. However, it's more useful for other purposes if you want to use it for other things too.
But for Sniffle, there is no difference?
No difference between the two.
Okay. Thank you so much. Really interesting talk.
Thanks. Yeah.
You said that equipment is rather cheap.
Yeah.
Have you considered using multiple devices to sniff multiple channels at the same time and avoid some of the problems that you mentioned?
That can be done. I actually thought of implementing that with 3 of these and just coordinating them in Python. It's cheap enough and can be done. However, just for the sake of convenience, having one device is nice, and with its ability to hop between these channels, you generally don't need it with Sniffle. With just one device, it can do it all. And you could even build a smaller, cheaper device. This development board here is rather bulky. However, the actual chip that does it is this tiny little thing here. So you could make a really tiny, simple, cheap board that did just that.
Hello. I have a question about active features.
Mm-hmm.
The sniffing is by definition passive, but
Yes.
then when you want to play with device, you would like to have some active possibilities to initiate pairings and play with all the options.
Yeah.
And one of the tools that Damien also proposed is a good start for that.
Mm-hmm.
What do you envision with the board and the capabilities of the tool that you are proposing?
So I had thought of implementing some active features in there, and it's fully doable. The radio here, it's fully bidirectional. You can do anything with it. So there are 2 types of things you could do. One is if there's an existing connection, try to interfere with that. And then the other is you just initiating connection to another device. Now, in my own usage, I found that if I just use like an app on an ordinary phone, like with a purpose-built Bluetooth stack. Most of this stuff is not too far outside the realm of the spec. Or you could even just do your own custom Bluetooth stack, but speak HCI with a normal Bluetooth controller. And if you're not trying to sniff traffic or do some other non-standard operations, it's often easiest just to use a existing ordinary Bluetooth stack to do that. It's just the thing where you need specialized hardware for and low-level radio control is when you're not acting as a normal peripheral or central device. As if you wanted to pair with something and you want to just see what characteristics it has or act as both a GAT server or client, you can just be an ordinary compliant device. Because this is not playing any of the traditional Bluetooth roles, this is why I need the low-level control. So, for active operations, there's jamming things, there's hijacking things, as Damian showed. These things have been done. In practice, I haven't actually had a need to do that, but I suppose active features can be implemented on this if someone wanted to.
Do we have any more questions?
Guess not. Well, thank you, everyone.